J'ai le plaisir d'annoncer Dr. Alexander Chaloupka, Managing Director from Netzsch Process Intelligence GmbH. This is, let's say, a very innovative entity inside Netzsch, because Netzsch is a very huge company, as you know, with several thousand employees. But this is a very innovative nucleus dealing with artificial intelligence. We will see later. And he came today with the business partner Ingo Schwarz from Schwarz Plastic Solutions GmbH. He's the managing director. I have the honor to welcome them now. I think you are starting. Mr. Chaloupka, right? Oh no, you are doing together. That's right. That's what you told me. Just a few words for Netzsch. It's a family-owned global technological leader with like 3,700 employees in 36 countries. So it's really a huge company. And the core competence is in analyzing and testing. They have more than 50 years of experience in material science, and through their technology, they are enhancing productivity. It's really very amazing what they have been explaining me before this conference, and I'm excited to really announce them to you. Artificial intelligence is the buzzword here in this presentation. And they will show us how you can really improve processes in efficiency and in cost productivity through using artificial intelligence. I won't hesitate to call you on stage. Please, gentlemen, go ahead.
Thank you very much for the introduction. Please raise your hands. Who is English speaking? Let's start with who is German speaking? English speaking? Okay, Ingo, let's do it in English. No problem. Okay, great. So, a little bit sad that we have around 10 people now. I think Corona is going to struggle us a little bit. Today afternoon, hopefully a few more people will show up the next minutes. So my name is Alexander Chaloupka. I'm coming from a corporate startup called Netzsch Process Intelligence within the Netzsch Group. And this is Ingo Schwarz. And today we will present you for reactive injection molding about what are the hurdles of reactive injection molding, what are the challenges we are facing, and how we, together within a collaboration with other partners, we will present you, are paving the way to transform reactive injection molding towards digitalization, towards a more reliable and successful part production. Do we have a pointer? I will do. Good. Ingo, some words to you and your company.
Yes, thank you very much. A warm welcome also from my side. I'm basically from the practical side. I was running an injection molding factory, actually 2 of them, in Spain and in Germany over the past 40 years. And since 6 years, I'm using that collected experience to put that into science and into large testing in order to supply solid data into artificial intelligence. And that's the reason why we are both here on stage today. We would like to give you an in-depth information of what we have started and where we are going to. Just to give you a little bit of background about our small consultants work we are doing every day. Basically, when a customer comes out of the industry with a metal part and wants to turn it into a plastic part, then we help those customers in redesigning the product, because you cannot just make black out of white or the other way. So there are some changes you have to do, like wall thicknesses and stress analysis and whatever. And basically we sit then as an external partner on the same chair or on the same table together with our customer and explain him and help him into the plastic industry. And the special thing about reactive plastics is that we are not only having a physical process on the material, like heating it up and then cooling it down again. We also have to consider chemical processes. And that makes our life somehow easy because the chemical process is overlapping the thermal process. And therefore, if you see the third picture here, the one here, it is very, very essential how the thermal behavior of our working tool, which we call the mold, how that is analyzed and controlled. Besides of that, we help the customers by doing injection trials, setup of molds, and also education. And the most important thing is characterization of materials, because no simulation really works well if you don't have the corresponding material card. And that is what we're doing also with the great help of company Netzsch.
So we as Netzsch Process Intelligence, we're the youngest company of the Netzsch Group. So we founded beginning or mid of August this year. So we are in a very early stage, but with a very big basement. We are setting everything up on. And we act under the brand name sensXPERT. As the name says, we combine sensor data and we collect all the data and proceed it within an artificial intelligence to generate information, to control the process, and to create reliable processes.
Now, as the headline says, thermosets are having some challenges. And as I mentioned earlier on, it is not just the physical transformation of the material, it is the overlapping chemical situation. And thermosets as such have a specific behavior. You might compare it to nylons, for instance, on the thermoplastic side. They are fairly nervous, I would call it like that, in regards to environmental influence. So sudden changes within your production area, like rise of humidity in case of a thunderstorm or something like that, or undefined storage conditions, today hot, tomorrow cold, and so on, have a large influence on the behavior of the material and on the processability. Besides of that, you get some typical natural things like an interruption of your process cycle. And think about the behavior of a chemical material. I would call it, it's sometimes like a wave. And if you interrupt the wave, it starts at a different height again, and you will read it in your product quality, and automatically you will have additional problems. And therefore, that leads into differences of the flow behavior, for instance. So your cavity, your body of the part will fill in a different way.
Yeah, and to show you a first introduction into what can happen during a production, here we show you an example of one and the same resin system. It's a SGL E420 SnapCure epoxy resin that has been cured within different states. So one time we've cured the pure resin. On the other hand, we have cured the same resin without additional additives in a glass fiber and carbon fiber prepreg. And what you can see here is that with one and the same resin, you have 3 different behaviors of curing. So you can see that the fibers have an effect on the cure process itself. So what we do sometimes today, or mostly today, is that we characterize a pure resin within the laboratory environment, and then we transform all the information into the production environment without taking into account that we have different fillers inside. And therefore, what Ingo has already said, this is one of the main reasons why today's simulations of polymer processing fails. And this is just the first introduction into how different material behaviors can be due to different fillers within a resin, but we will show you more examples later on during our last, or we've created during our last session a few weeks ago, during reactive injection molding.
Yeah, in fact, as you see, both of us did trials based on epoxy resin. This is a resin where very much experience is already there in the market and where you can interpret the signals easier than if you have materials where some add-on basically reactions are happening during the process. This is why we started with it. In that particular case, we were using a granular material from the material maker Ruschig in Ludwigshafen called Epoxydur EP3585. That material will be used, for instance, for encapsulation or for just single parts which are molded. And you can use compression molding, transfer molding, and injection molding processes. It's a material which is pretty stiff compared to thermoplastic materials. It has a filler content of about 70%. So, and that's the surprising thing compared to thermoplastic materials. The filler content is much higher. Therefore, the resin or the polymer content is fairly low, and still the influence is extremely high on the behavior. The idea behind is making sure that under all production circumstances, the future generation will be able to work with those complex materials. Why is that so? The customer wants to have security. He wants to sleep well when he has placed such a product, and go into automotive or aircraft industry. Nobody wants to have a risk. You want to have something which you can rely on. Your car shall last 8 years or 10 years without a problem, and therefore the manufacturer doesn't want to see the car back in the factory or in the garage. So therefore, they want to be safe that whatever product is designed on it, and it is an ideal material to replace metal. Therefore, it is a lightweight solution. However, you need to know how it works, and there is the problem. We are getting more and more problems in filling our shop floor with well-educated staff. So we have to see how a 24/7 production, so 24 hours a day, 7 days a week, can be filled with the adequate people. And as this is more complex to the overlap of chemical and physical activity of that material, it is important that the feedback to the process by the machine, by the mold, is as good as possible so that the employee who works with the machine can rely on what the information is. Today, this is not the case. Today, you get all kinds of informations, but they are not detailed enough so that the worker, Sunday night in the night shift, can be sure that his machine is running on the same level than on Monday lunchtime when all the staff of the company is there. And this is why we need artificial intelligence, why we need to collect as much data as possible about variations in process. So, in other words, we want to understand the process by a huge amount of data. And to give you a number, if we do trials in molding for 1 day, we easily collect something like between 10 and 20 gigabytes of data. Gigabyte. Think about that. And now you need to pick out of this huge volume of data the correct data to give the feedback to the machine, to the process, and to the worker what needs to be adjusted that it works well. And that's exactly what we want to do on the production side. At the same time, we also need to give that information back to those in the supply chain who prepare our equipment. That can be the machine manufacturer. It can also be the mold supplier, the mold maker, because they have a lot of experience, but it's experience. It's not really calculated. And this is why in the beginning I was talking about thermal simulation, for instance. You need to know what's going on. Nobody would put a cake into the oven and hoping that somehow the oven would work well. You have a very precise idea of what the temperature should be like so that you get a good cake out of it. And in principle, that kind of production is very similar to it. So we want to find as many materials as possible under the most variable conditions in production, take the data out of it, and give the content back to the potential users, to the customers, so that they can then work on a higher level. To be able to do so, we did quite some large investment together with other collaboration partners. So we invested into a 240-ton injection molding machine, which has variable injection funnels. So we can go from small volumes up to very large volumes. Those large volumes with something like, let's say, 2.5 to 3 kilograms piece weight are intended, for instance, for the electromobility, where electrical engines need overmolding. And we can do the whole variety of thermosetting materials on that machine, plus additional process details like, as we call it, the core compression technology, which gives us more stable, more reliable parts. And the interesting thing is, here underneath, where all the electronic stuff is installed, there are some open channels, in total 8 of them, which can be freely selected between all the parameters of that machine. And those data coming out via cable. We cannot put that into Bluetooth. We need the cable still. They are then driven into a big cloud of Netzsch, where then the computer scientists, I would call them, are finding their ways how to select the most important data out of a real production cycle. So we are not playing somewhere in the air. We are doing real production conditions like we see it with our customers, like we do it out of our own experience, send it up, and then under the hood of Alex Chaloupka, it will be selected, condensed, then we verify it together, and then we prepare it to our dear customers. And that is not enough. In addition to the machine, we also need a mold, as you can see it here. And with that mold, we can do the typical scientific specimen for any kind of test bars or plates or so. But we also have some specific other inserts in that mold. All of them are equipped with a variety of sensors, temperature sensors, pressure sensors, and the dielectric sensor, which is the most important one in that case, because we are able, by the technology of Netzsch, to determine whether a project is, or a process cycle is finished or not. That means, let me say, to the oven again. I take a normal cycle time of a cake for 1 hour. In that case, we drive down the cycle time to 30 minutes. If you look into your cake, typically the inner core of the cake will be soft still. It's not completely baked, or as we say, cross-linked. The other thing is, you put it on for 1.5 hours, and then all of a sudden your cake turns from brown into almost black. Nobody likes that. On thermosetting material, you don't see that. But you will see it on the cost side, because it's much too long in the cycle, and you will see it also in the quality of your material. That is why we have all these reading and intelligent equipment installed, and that gives the stability and the quality into the cloud.
How we do that? We have connected our package to the machine environment. So we have an edge device created by ourselves where a huge software package is running on, also equipped with artificial intelligence, where we collect data from sensors out of the mold and we collect the machine parameters. On the same time, during collecting the data, our artificial intelligence algorithms are running and calculating quality criteria of the material, like glass transition temperature, like degree of cure. And we can also follow a different mixing ratio, like baking your cake, having different amounts of constituents, we can see the difference. And therefore, we can, based on the information our artificial intelligence model has, we can readapt the process to create a good part at the end. After collecting the data, we transfer them to the cloud environment that acts as the storage system, but furthermore also as the global artificial intelligence platform, because here we have more or less unlimited space, and therefore we have a huge amount of data we can store in the cloud environment. It then can be used to readapt the machine learning models and to continuously improve the model we are using. What we, in principle, do is we collect data from 3 different sources during the production environment. So we use the machine data, we use the cavity data, so sensor data out of the mold, if it's our dielectric signal, to collect data from the material behavior or pressure or temperature sensors. And we also use material data. Here we talk about reaction kinetics, the physics and chemistry behind the behavior of polymers. And combining all the 3 different sources of data, we are in charge of seeing the dependencies between process parameters and material behavior, and therefore are in charge of readapting the process due to different states of the material. When we have a look to artificial intelligence, what are the prerequisites we have there? There is a high need of creating a huge amount of data to be able to have the basement for the statistics artificial intelligence is using. Therefore, we need a huge amount of data we will never get from a real polymer production plant. So there is no chance to install a package and to follow the process for 6 months, 12 months, or for a longer period to get enough data to create a machine learning model that is capable of readapting the process in terms of creating higher part quality or reliable processes. Therefore, we have our own way on doing artificial intelligence. We simulate our own data sets based on reaction kinetics, real process data from the environment we are installed into, and we combine current quality criteria of our customers, whether it is degree of cure, determined with a differential scanning calorimeter from the lab, whether it is the elastic modulus created via dynamic tests. Whatever our customers having as a standard today, we can use, and we can simulate the data sets behind that we need based on the first measurements out of a real mold combined with material science to be able to simulate different states of the material. Therefore, we are in charge of varying temperatures in a simulation environment and also humidity to create a huge amount of data sets to see the dependency within different states of the environment. We have a very high bridge or a very long bridge we have to gap between laboratory environment and the process environment, because the laboratory environment is nothing but the same like a process environment. So we have temperature deviations within the process environment we will never see in an isolated environment during a lab characterization. And we have material deviations we cannot really follow. So there are material deviations, batch-to-batch deviations that occur during the manufacturing process. We have to react to them. And that is what we do.
Now, what we do today, I wouldn't go that far to say we do trial and error, but in many cases we do it because we do not know a lot about the material, especially about lot variations. And therefore, it is important, and Alex has underlined that we do not work in somewhere in heaven. We work with the feet on the ground, with real parts, with real processes, and with variations of these processes. Therefore, we will check, and you see the product here on the side, with, let's say, a case or a box, whatever you want to call it, with different wall thicknesses, with different gate positions, because all of the 4 gates can be either opened or changed. So we can really do a lot of different process variations with, in that case, one complex mold. And therefore, we can find out what happens in the real life when cycle times are too short, when injection speed is too high. That means too much shear and therefore too much heat comes into the reaction process, and you get a sudden cross-linking, which you would like to avoid usually. So therefore, in that first trial which we did, we varied the injection time equals injection speed by standard time, which would be 4 seconds in that sample. We doubled it, and we did 50% of it. So very strange extremes. And we also varied the mold temperature only a little bit to see, do the 5 degrees have an influence? Or are we believing we might overdo the whole thing? Interesting, we can also vary our film gate. That means we have a thicker entry of the material, so it basically is flowing in like chewing gum. Or we have a very thin gate where it's heated up so fast that the material almost comes in like water. And finally, we did the same material, but we took different bags, because out of experience, we know that even one bag to a second bag might have a big influence in the processability.
And that is what we want to show you now with the next 4 slides, with the deviations we've done and we've performed to see the difference between pure reaction kinetics on the left side and the real material behavior we've measured within the mold. So you can see that varying the injection times, in theory, there should be a shear change and therefore a different temperature state within the material that enhances the cure speed or lowers the cure speed. And that is what we can really measure. You can see here on the right side. But with pure reaction kinetics, like simulations are done today, or lab characterization, and then transforming the data with pure reaction kinetics to a process environment fails in this case, because here we cannot see the difference that really occurs. On the other side, when varying the film gate, here we also have a different behavior of shearing and temperature influence. And also here we can see, in this case, reaction kinetics and real material behavior fit quite good together. But when we change the material back, on the left side you can see pure reaction kinetics just based on the temperature measurement within the material that cannot see the back deviation, back-to-back deviation. But we can see it during the manufacturing on the right side. So here we really have the chance to make a change within the process environment and to teach our artificial intelligence how to react on that and how to readapt the process. On the same side, we can see
I'm sorry that I'm interrupting you.
We are very close to the end.
Because if we want to do Q&A, we have to, otherwise, because we have to close at around 6.
That's the last example. So
fine.
we are very, very close to the end. Here, a change of just 5 degrees C in reaction kinetics should make a big change. but we can see in the real material behavior, it doesn't. So we have a slight change, but not that dramatic like we've expected based on pure reaction kinetic simulations with the basement of laboratory data. So therefore, we will enhance our activities in the future to create more information, to get more specific in what parameters from the machine have a really big influence on the material behavior, and to further train the artificial intelligence and to feed it with a database of different materials to give our customers the chance to have a reliable process without the knowledge of experts in the field of thermosets. So thank you very much.
Thank you,
and
Alexander.
Now we are open to your questions.
First of all, I have to say it was an excellent presentation. I mean, every presentations were good and excellent, but it was really outstanding. No, I have to tell you, because it was so clear for even somebody who is not really maybe familiar with artificial intelligence, was really very, very nicely explained. I want to ask you a quick question, because are you offering prototyping and testing for the experts, for the industry, for customers? I guess so.
That's a question for you, Ingo.
To precise.
I'm sometimes struggling with the name prototyping. Yes, we do trials for customers, very intensive trials even. So we can even use existing molds from the customer. And provided it's acceptable, we can then even put the sensors inside. And by that we can support everything. But it is not the typical prototype like you do it with a printer, making one example only. Okay. That does not really work in a series production. So we focus on series productions, and we want to make your life more stable.
Okay, thank you so much. Is there a last question from the audience? Would you like to get explained something, or maybe you are joining the gentleman at the booth, I would say. I have another question, but I think we have to close. I would come also to your booth and ask the question. Thank you very much for this excellent presentation, and unfortunately we would have wished to have really the hall with plenty of people coming from everywhere, but this is Corona. We have to deal with it. It was a very nice audience nevertheless, and thank you so much.